believe I just went live. Just checking things. Okay, I think I'm live at the moment. I just need to make sure I get the chat on. Just want to make sure I get the chat open. Okay, let's see here. Sending myself a link to the Hangout or the chat that we got going on. Apologize if you hear any strange noises, by the way, while we're doing this. Okay, let's see here. Just making sure everything is all hunky-dory, because I want to make sure if anything comes up during the stream, if anybody has any questions that they can ask me. Let's turn down that. Okay, I got that open. Just getting things all set up here. Note that I will have I'll have access to the YouTube chat, which I'm going to just make sure that I link. Just one more thing. Just got to send out one more thing. Okay. Okay. So let me get things here. Okay. So this is technically the first stream I'm experimenting with the new dolly rig system. So we're going to see how this goes. Let me know if you're watching this, how the audio is. Note that I only can see the YouTube chat. So just keep that in mind. So today I'm going to be talking about a concept called smoothness. Now, you might ask, damn, what the heck does that mean? Well, today we're going to do kind of a shorter stream, depending on how much time I have here. I'm going to be talking a bit about this concept called smoothness, which is often, I find that some schools like covering it, some don't. I find it's one of those things that just doesn't really get covered a whole lot, and I really want to kind of give it a little bit of focus so people can learn a little bit about what this thing is, because it actually is a very helpful tool. And a lot of the time when you see or encounter more advanced material, sometimes the presenter or lecturer or whomever is doing the work in front of you will make assumptions based on smoothness. And sometimes students ask, well, how can you make that assumption without having to do a whole bunch of extra work? Well, the goal here is I'm going to be trying to show you how you actually do that. Okay, so I can see the chat, awesome. Yes, Javi, yes, I gotta get some smooth shots in. Once we move from this board, I'm gonna move over to that board back and forth. So just keep that in mind, and I'll try my best to answer if anybody has any questions or anything like that. It's worth noting my computer is right here, my tablet's down here. So if you're wondering why I'm looking down, that's why. So you're up here right now. So if anybody isn't aware that I've been building up a better setup. So there's a new dolly system which the camera can move left and right on. Well, left and right on. And we'll be using that just for this guy. Now, if you aren't patient enough and you don't want to watch me do this live, I will be editing any of the content that I'm going to be presenting here into individual videos. And those will be put up on the channel. So just keep that in mind. So if you find yourself watching this and you're like, oh, I don't have time to watch a live stream, don't worry. You'll not miss out on any of the main stuff, except for fun bloopers, because that's inevitable in the land of live video. So just keep that in mind. So anyways, with that being said, we're going to get started here. So just like I said, this is going to be, I'm probably not going to be able to cover everything I want to involving smoothness. So if I don't finish it up here, I'll be finishing it up in either later or tomorrow probably. So I have a lot of examples I want to do. So we're going to have ourselves a good time here, and hopefully by at least the beginning of this, you'll have some understanding of what smooth means when we talk about complexity functions. So you'll find some versatility with this idea, because a lot of time, like I say, it tends to get glossed over unless you have a very diligent theoretician or they have time to cover this thing. Because it is a very nice analytical property that a lot of functions that people study in computer science use all the time. So anyways, we're going to talk about this concept called smoothness. So here's the idea. I have myself some complexity function, and I want to know its asymptotic behavior. So we've been talking about big O, but we're going to just talk about what does that mean when I consider, say, parts of the input. So when I mean parts, I mean some subset overall of the input. So what do I mean by that? I mean, if I give you input n to my function called f, so if I get the value, it's called f of n. What if I did it where I only considered inputs for which they are some power of b? So if I give you, if b is equal to 2, it's 2 to the power k. So for example, inputs like that would be 0, sorry, not 0, it would be 1, right? Because 2 to the power 0 would be 1. 2 to the power 1 is 2, so powers of 2. Or if b was 3, it would be powers of 3. And as long as b is some fixed integer that's presumably positive, we're going to be interested in forms that are going to look like this. However, it need not necessarily be that way, but you have to be careful. But we're going to focus mostly on this case because when we do analysis of algorithms very often, we're very much interested in situations where we want to say something about integers that belong on the powers of 2 very often. So for example, you might run into this when you analyze the running time of an algorithm such as binary search, or if you talk about, say, merge sort would be another good example. So sometimes people like to simplify their analysis by assuming n is some power of 2. I'm going to show you the kind of the theoretical framework that allows you to make that assumption and still say broad statements about the complexity of the function, regardless of what n is. So what do I mean by that? We're going to consider some complexity function f. Sometimes I'll call it g, depending on what we're using it for. And what I want to do is I want to come up with a very simple set of conditions. So if I told you that f is big O of g on some restricted inputs, so some simpler case, such as n is a power of b, where it's like if b was 2, it's all the powers of 2. I want to be able to say, if I know that, then I can say that f is big O of g for all n. So for all the inputs, or for all the domain, if we want to get technical. So that's the general gist and the idea here, is I want to be able to say, if I give you for some subset of the inputs over the entire domain, I want to be able to say something about the big O for f over all of them. That's the idea. It sounds a little strange at first, like, okay, well, why would you want to consider when n is some power of 2? Like I said, if you encounter cases such as analyzing algorithms for things like binary search, like I said, divide and conquer algorithms, you'll find very often this assumption gets you a really far way. We'll actually see an example either today or when we get to the rest of this of how we can actually use this concept to simplify analyses. Now, you might ask, Dan, what's this word smoothness? So I'm talking about smooth functions. Now, in the context of analysis of algorithms, this smoothness in this context is referring to when I restrict the inputs like this, where n is some power of b, I'm only considering parts of the domain. So all the possible inputs, I'm considering some subset of those. The concept of smoothness is that if I want to say something about it with this restricted set of inputs, I want to be able to say it for all of them. So if, say, for example, I consider the powers of 2, like say these were the powers of 2, and say if I was plotting, now naturally this is like on a log kind of plot. If I sampled all the ones that are powers of 2, for example, I would like to know that there's some behavior such that I can propagate. I know that that's going to be true for all of them, so I want to propagate over all of them as opposed to just the powers of 2. So that's what the concept of smoothness. So that's what smooth means in this context, is that I can make statements about parts of the domain, so powers of b in our case, and then what I could do is I can propagate it over all of the inputs. That's what it means by smooth. So hopefully that's clear. So, just to summarize, we're going to be interested in these complexity functions where we have some set of inputs we're going to restrict over. So, we're going to be interested in when n is a power of b. It doesn't have to be that, but I find that this case is one of the ones that most people are interested in. Yes. So, yeah, I mean, that is correct. So, we're talking about the idea of, so we're saying that the behavior of the function doesn't oscillate like crazy, like it doesn't go like this. Instead, what it does is it follows along. So if I sampled across the 2 points that I sample over, like these powers of 2, I know the behavior isn't going to go like this. It's not going to go insane. It's going to follow along. If I were to take a sample like this and maybe drew out the chart really wide like this, and imagine if as the chart looks like it's rescaling and getting shrunken down, if I draw a line across those, you'd agree that they would look like lines, right? If I make it and rescale it and keep expanding out what the, say, one of the axes, and I stretch it out, it'll look smooth. That's the idea here. That's at least one way you can think about it. But yeah, it's indeed about the predictability of this function. It's not, I don't mean that maybe in a statistical sense. That's not really what I want to talk about here. It's more that I can say things about the domain like this and still say things about the general function. That's all I really want to say. So I say things about parts of the input, I get it across the whole thing, which is, it sounds really strange at first, but I assure you it actually does have a neat application. Okay. So anyways, let's define what that means. So let's talk about what a smooth function is. So here we go. Let me give you the definition of smooth that we're going to use. And it's going to look a little strange. It's going to be a little strange. See, like I said, this is the fun camera here. Okay. So we're going to define what is called a smooth function. So let's define smooth. It's a little squeaky. A complexity function. So this is going to be a complexity function. If you don't recall what a complexity function is, the way we defined it is it's a function that's never going to become negative. It only works on inputs that are going to be positive n integers, and it keeps some number that isn't going to go negative. It could be 0 or up, but it can be like fractional numbers. If you want to be more exact, real numbers. Okay, so a complexity function that is both. Now, here's the first word I have to lay out here for you. It's something called asymptotically non-decreasing. So it's both asymptotically non-decreasing and f of 2 times n is, or is in, big O of f of n. Okay, so now what we got here, so we have two conditions here for what we, so if it satisfies both of these, we say the function f is smooth. So let me break down these two things. So the first guy here is asymptotically non-decreasing. Now believe it or not, we've actually encountered the idea of asymptotically non-decreasing before. Just, it's actually buried inside of the concept of big O. So if you don't recall, asymptotically non-decreasing is simply this. So if I want to say that if, so first, we need to talk about two things. First, there's this thing called asymptotically. Some people like to use the word eventually. I like to use either one. So if you hear me say eventually non-decreasing as opposed to asymptotically non-decreasing, they're the same thing. They're the same thing. So asymptotically means for sufficient n, or input, and this non-decreasing part means this. So I'm just going to give you a little aside. So I just want to say what asymptotically non-decreasing is. I'm tempted to switch markers. Non-decreasing. I'm going to switch markers. This one's a little squeaky. Okay, so asymptotically non-decreasing, what does that mean? Well, it just simply means this. So first, let's just tackle the non-decreasing part. So non-decreasing, normally when somebody asks you what non-decreasing means, it means that, okay, if I give you f of n, it has to be less than or equal to f of n plus 1. So it means that if I give you some input n and I feed it to the function f, its output is a non-decreasing function allowed to kind of like do this? Or does it do something more like that? Or does it do something like this? Well, it'd be more like these last two here. Non-decreasing just simply means it's not going to pit down like this. So if I give you some input n, the next input I pass along, it better be that the output's going to be either the same or larger. That's all it means. So that's the non-decreasing part. So it just means that when I plot the function, it can go like this, it can stay the same, or it can get bigger. It can't pit down like this. It's really just that simple. So now I need to actually give you the condition here, because I didn't say anything about n, right? So the asymptotically, this is why sometimes people use the word eventually, is that there exists n0 such that this holds, this inequality holds for all n greater or equal to n0. This shouldn't look too alien to you because this looks, it's an aspect of the big O definition. So notice that this is really just me saying, okay, at some point, this inequality has to hold for n. So n could be n0 or it could be bigger. And note that n0 here is, we're just going to assume it's a positive integer. I'm using that fancy z to indicate it's an integer, with the plus meaning positive. Okay, so hopefully this is understandable. So remember, the function, all these functions that we're going to be interested for smoothness all have this property. So they can go up like this, they can level, but then they can't do this. They only can go up or level. That's it. So that's the first part, asymptotically non-decreasing. That's just one element actually of the big O definition. But it gives you the strict property right here that's in relationship to itself about f. So there's this part. The second part looks a little strange at first. It says f of 2n is big O of f of n. Now, you might ask, Dan, well, shouldn't it be that if you say something about the original function, that it's guaranteed that it's big O of that thing, because it is that function itself? Well, if I remove the 2, this is actually a true statement. I haven't proven it for you, but I will in the future, that the big O has the reflexive property. Reflexive means that if I give you the thing, it's guaranteed to have the property. That's it in plain English. So if I said f of n is big O of f of n, that is a true statement. However, this isn't necessarily true for any complexity function. Only specific ones actually have this property. Okay? So this is what a smooth function is. It's asymptotically non-decreasing, meaning that there's a sufficiently large number n0 such that every input that is bigger or equal to it, it must be that you get this behavior over here where it either goes up, levels, but it never goes down. Okay? So that is the definition of smooth. Now there's many different kinds. Now you might ask, Dan, well, why does this matter? Well, as I said, there's a beautiful trick you can do that gives you this relationship right here. But it only applies for certain kinds of functions. And they happen to be a lot of the ones that computer scientists tend to be interested in. So I'm going to give you some examples of functions that are smooth. And then we're going to actually do some examples where we actually prove that they actually are smooth. So you can actually get a flavor of how you actually prove these claims. Okay, so for example, I'm just going to give you just a list. So any constant function. So constant functions, they're smooth. So anything that's in big O of 1, that is a constant function. Any one of these guys inside of here. So this is the set of all constant functions. Well, constant complexity functions. If they're one of these, they're smooth. We're going to prove that actually in a moment. So other ones include logarithmic functions. So we talked about logarithms at one point. We're going to definitely talk in the future a lot more about logarithms. Logarithmic functions. So big O of log n, or if you want to put the base 2 in, you can, but as I'm going to explain in some future event, I'm going to explain that the base doesn't really matter a whole lot, as long as it's a valid base. Other things like polynomials, we've talked about polynomials before. Please forgive the writing of polynomial, it looks like it's melting in the microwave. So, polynomial functions. So these are things that look like n to the k, where k is a constant. So these are examples of functions that are smooth. Now you might ask, Dan, give me an example of one that actually isn't smooth. These are all smooth. So all these are smooth. However, one that isn't smooth are exponential functions. Oh man, the writing is just so bad here. Exponential functions. So for example, things such as 2 to the power of n. This is not smooth. Not smooth. So exponential functions are actually not smooth. So a lot of the ones that computer scientists tend to be interested in usually are smooth. And so if you know, for example, if you know something about g, for example, and you know it's a smooth function, you'll actually be able to say something that's very interesting. I don't want to spoil it quite yet, but these are examples of smooth functions. So hopefully the definition is clear. So just remember, we want some function that has this property. And keep in mind that most complexity functions, if not almost every one you might encounter, will be some asymptotically non-decreasing function. Not all, I can't say a not all statement, but most things that you encounter when you're analyzing algorithms will be an asymptotically non-decreasing function. So usually when you encounter these things, and when it's unclear is when we actually have to deal with more complicated looking functions such as recurrence relations. We're going to talk about recurrence relations some point in the future as well. Okay, so that's the concept of smoothness. So that's what smoothness is. Okay, we're going to do some examples because I want to actually show you how you actually show a function is smooth. So we're going to prove, we're going to actually look at each one of those on the right hand side, and we're going to prove that those functions are in fact smooth. So it's worth noting that if you can't see them, they're the constant, logarithmic function, polynomial function, and we're going to show also that the exponential functions are not smooth. We haven't really seen any of those examples quite yet. But anyways, we're going to prove the following function is smooth. So we're going to let d be some positive real number. So this means that d is in the set of all positive real numbers. So we're going to prove that function f of n equals d is smooth. So this is indeed a constant function. We're going to prove that this is smooth. So I'm going to give us the game plan. And once you understand the game plan, this is going to actually be not too bad, actually. So I just want to remind you what the definition of smooth is. So let me just remind you of the definition of smooth. So while I'm chatting here, the game plan is, remember, to show a function is smooth is that we have to make sure it's asymptotically non-decreasing and f of 2n is big O of f of n. So remember, this is the big strategy that we have. If we can show that both of these properties hold, we're done. Okay? So anyways, let's get started here. So what do I usually do? What do I usually do? What's the usual thing I do? Well, I say what I'm going to do, right? That's normally the plan. So let's do that. So the first thing I'm going to point out, and you're going to say, Dan, this is sort of like cheating. Do you look at this function and say, hey, look, is this eventually non-decreasing? And the answer is just yes. It has to be eventually non-decreasing. Now, that being said, I'm just going to repeat myself for each one of these examples just for clarity. But for all the functions that I'm going to prove smoothness for, they're all eventually non-decreasing. You can actually use mathematical induction to prove that. But I'm not going to do that here. Instead, I'm going to reserve proving those kind of claims in the future for more complicated functions such as recurrence relations. Just because we know and have encountered things of that nature several times in our examples, I'm not going to push that burden on. I can push that burden on to you. So what we're going to prove is we're going to have to prove the second condition, that f of 2n is big O of f of n. So just for the sake of completeness, I'm going to say that, notice that f is asymptotically asymptotically non-decreasing. Like I said, I think that showing this is quite... I don't like to use the word obvious because that is a no-no in mathematical reasoning. You don't just say something's obvious. You can't just say that. It has to be true for some mathematically deducible reason. So I would recommend, if you wanted to prove this claim, I would recommend using, well, one, you could see right away that this is just going to be true regardless of n, because d is independent of n. So no matter what n is, it's going to be exactly equal to d. So notice that f is asymptotically non-decreasing, because as n, so regardless of what n is, it's always d, which means that f of 1 is equal to f of 2, f of 3, f of 4, f of 5. All of them are equal to one another, implying that it's eventually or asymptotically non-decreasing. Now, I must stress, we might encounter a cat. There is a cat sitting on that chair over there. So if you encounter or see a cat, please forgive me. They are rascals. Okay. So I'll just say here that f of 1 equals f of 2, and so on. F of I for all n greater or equal to 1. That's one way you can deduce this. But you can also prove it by induction if you really want, but don't worry too much about that. Anyways, so now with that condition out of the way, we're actually going to get to the meat and potatoes. So what do we need to do? We have to prove f of 2n is big O of f of n, which means that we need to find constants c, which is a positive integer, and n0, which is a... Sorry, that's a positive real number. That is a positive integer. Such that... That's supposed to say such that, but I'm just sort of running out of space here. Such that... The cat's watching. Yes, you stay over there. I see you. Okay. So we need to find constants c and n0 such that for all n0, f of 2n is less than or equal to c times f of n. So notice all I'm going to do now is I'm going to plug in what f of 2n is and what f of n is. So what is f of 2n? Well, notice that f of 2n, remember, I said that it's equal to d for every single possible input, right? So this is, so if I just plug it in, so I'm just using if and only if because I know what f is, so I'm just going to plug in f into both sides of its inequality. So if and only if the following statement, d, so that's f of 2n, this is less than or equal to c times d, which is d is f of n. So we're going to just pick c. There's a cat doing things over there. Miss Kitty, don't you be doing that. I'll get you the spray bottle. Miss Kitty, get away from there. That cat is getting immune to the spray bottle. The cat is climbing over my equipment. That is kind of a big thing. So we're going to pick c is equal to 1. Then what do? Well, I'm either going to make some observation probably, or I'm going to say what I'm going to do next, right? But this is a really straightforward thing. Now I have this right here. So if I pick c is equal to 1, what does this turn into? What does that turn into? then notice that both sides of the inequality are equal, right? For all n greater or equal to 1. Do you see that? So if this becomes 1, then it's just d is less than or equal to d, but d is equal to d. So this inequality has to hold, regardless of what the input is. Okay. So what am I going to choose? I'm just going to choose n0 to be equal to what? Equal to 1, right? We want it to be equal to 1. So, therefore, by the definition of big O, D is in big O of D. And what does that mean? And what does it mean now? I have both the properties, right? So I know it's asymptotically non-decreasing, and I also know that the big O, the second condition, also holds. So that means that and f of n equals d is smooth. And we're done. La la la. It's, like I said, it's nothing too complicated, because we've done some examples of proving claims involving big O, actually. So it's really not that sophisticated. All we really need to have is we're just proving another big O claim. That's why I want to show you this, because you know how to prove big O claims, right? The only thing is now this new property involving the asymptotically non-decreasing, and also the fact that now instead of us looking at just some f of n and g of n, now we're looking at f of 2n, where we just substitute wherever you see n, you put 2n in, and the right-hand side is just the same function. Okay? Okay. So, while we do that, I'm going to Okay, let's get to our next example. Okay, just want to make sure there's no questions. I think we're good. Let me take a peek. Okie doke. Okay, I think we're good. Okay, so we're going to do another example here. Now, what we're going to do is we're next going to prove the following. We're going to prove that function f of n equals log base 2 of n is smooth. So we're going to prove that a pretty standard logarithmic function is smooth. I'm a little close to the top there. So we're going to adopt the same strategy we did last time. We're going to make sure that we use the second condition of the smooth definition. We're going to prove that directly. As I said, logarithms, polynomials, these are all eventually non-decreasing functions. I'm going to take that as a well-established fact. But like I said, there's not too many hard properties you can point out to make and show that these actually are true. So I'm just going to take as a given that the logarithmic functions are all eventually non-decreasing. So I'm just going to proceed and say that I'm going to say observe that f is asymptotically non-decreasing. So what we're going to do, so we have f is asymptotically non-decreasing. So I'm going to take that as a fact. Like I said, it is not, you should never use the phrase, or at least you should avoid using the phrase, it's obvious. It's a mathematically true statement. So you can't just say it's obvious. It has to be that there's some reason for that. So what we're going to do is now prove the other condition. So remember, I'm just taking this as a fact. If somebody asked you to prove this, you would not just say observe that it's eventually non-decreasing or asymptotically non-decreasing. That is not an acceptable form of proof. Okay. So what we're going to do is we're going to let us find constants C and N0. Yeah, we're live right now. Yeah. Yeah, what's up? Yeah, what do you need in the fridge? Lettuce. Lettuce. I'll get you lettuce. We're getting lettuce. I'll be done here in a moment. Lettuce, lettuce, lettuce. Lettuce. Sorry. No, it's okay. Okay. So we need to find constants C and N0 such that f of 2n is less than or equal to C times f of n for all n greater or equal to n0, right? That's what we usually do, right? So what are we going to do next? What do we need to do? Well, we can either pick our C or N0, but maybe it might be a good idea to plug these in. So perhaps maybe even writing after this, maybe even writing the if and only if and saying at log base 2 of 2n is less than or equal to C times log base 2 of n. So this would be what you would replace this with. So remember, wherever you see n, you put 2n. Wherever you have n, just leave n. So what are we going to do? Well, I suggest that we pick C is equal to 2, and you're going to see why. Pick C is equal to 2. Then we determine N0 such that the following. What do we need to prove? Such that for all n greater or equal to n0, log base 2 of 2n is less than or equal to 2 times log base 2 of n. Now, this is where things are going to get a little interesting for us. What we're going to do is we're going to use a property of logarithms. Now, does anybody see anything that we could do with this logarithm here? This logarithmic term? There's actually a nice property about logarithms that we can use to dissect the left-hand side of this inequality to make it a little easier for us to play around with. We're going to use something called the product rule of logarithms. So we're going to write that over there. So let's give me a moment to erase the board. Okay, so while we're waiting here for one moment, I want to point out that a nice property of logarithms is that if you have a product inside of inside of the input for the logarithmic function, you could split it on products into addition. That's going to be effectively what we're going to use here. So notice that by the product rule of logarithms, now I'm going to start on the left-hand side. You find that this will be a little easier to play around with when we do that. So I'm going to start with log base 2 of 2n, which by the product rule of logarithms, this is a product here, it's 2 times n. The product rule of logarithms allows me to separate this into 2 logarithmic terms over a sum. It has a corresponding relationship with exponents. Like I said, we haven't written out a proof for this property. We'll maybe see it in the future. But so log base 2 of 2n is equal to log base 2 of 2 plus log base 2 of n. Now, usually when you're writing down these chains that reach the right-hand side of the inequality, I suggest writing down reasoning. Otherwise, I suggest writing down your reasoning on the right margin. It makes things a little easier to follow. However, if you can't do that, or if you need more space, please just write down a sentence that connect the 2 inequalities or equalities that you're writing down, okay? I suggest doing that so it's clear for the reader. So this is the left-hand side of the inequality. That's what it is. And then we apply the product rule of logs or logarithms. That's what we're using here. Now, if you remember the definition of a logarithm, you remember that remember this is the inverse operation of exponentiation, right? So I want you to think, if I give you a number like, so I know the base is 2, so I have 2 to the what is equal to 2. So actually, let's write down y here. What should y be equal to in order to be equal to 2 here, if we're assuming y is positive? What does it need to be? It needs to be what? It needs to be, it's 1, right? Because 2 to the power of 1 is equal to 1. So this is equal to 1. Then I'm just going to leave the log base 2 of n there. This is because log base 2 of 2 is equal to 1. Then, now this is where we're going to make that jump in our reasoning. So Be very careful here. So what I want to do is I want to make a logarithmic term that looks like something that's a 1 or larger, because I know that we're going to be considering such. I want to make whatever on the right hand side look like logarithmic terms multiplied by some constant, right? We used the strategy before. Just I gave you a general recipe for it. So I want to replace this 1 with a log base 2 of n, right? That's at least what I think might make more sense. Now, I want to ask you a question. Well, how big does n have to be in order to make this work? Well, I can tell you that logarithmic functions are increasing. They're increasing functions. So if I told you that log base 2 of 2 is equal to 1, would you agree with me that if I put in, say 4 into the logarithmic function on base 2, that would be equal to 2, right? If I use 8, it would be 3. 16, it would be 4, and so on and so on. It gets larger, right? So what value for n should I use here? I should use 2, right? Because we know log base 2 of 2 is equal to 1, right? So I'm going to use the fact that we know that log base 2 of n is greater or equal to 1 for all n greater or equal to 2. That's how I get to this step. You can't just say statements like this without any domain otherwise, unless you know it's true for every possible n. Okay? So all I did was I took these two terms, brought them together, and I noticed there's just 2 log base 2 of n terms. I'm getting really excited here. And so we get 2 times log base 2 of n. And that's exactly what's on the right-hand side, right? And this is for all n greater or equal to 2. So select what? What should I pick for n0? So select n0 is equal to 2. And we're good, right? Therefore, by the definition of big O, log base 2 of 2n is big O of log base 2 of n, and log base 2 of n is what? It's smooth. And we're done. So this is how you could prove that the logarithmic function, so if I give you a logarithmic function, it'll generally follow this similar strategy. The only thing I took as a fact is that logarithmic functions are, in fact, asymptotically non-decreasing because they actually are increasing. They always increase. If you need an intuitive way of thinking about it, is that imagine, remember I told you that the definition of a logarithm is if this is the input on the right-hand side here, y is what I want. So if I want to get a larger input on this side, what does the base have to be raised to? A larger exponent. Okay, so that's how you can visualize this. If you need something to kind of realize that, yeah, even if it looks kind of like a cute little curve thing, it still increases. Okay, so this concludes this example. So what I'm going to do is I'm going to wrap things up here, and I'll be doing more examples maybe tomorrow. We'll see. We'll see. So, because we still got quite a bit. I have a lot of fun things here. So when we come back, we'll look and actually find out what exactly this concept of smoothness gets us. So remember, the big game plan for us is to get it so that we can say statements about complexity functions where we have domains that are restricted so that like n is a power of b, where b is some fixed integer. But I want to be able to say things about that, and in consequence get the general complexity regardless of what inputs I assume. Okay? So I think that's everything. So I want to say thank you very much, and have yourself a beautiful day.